Hello everyone, my name is Bishoy Essam, and today I would like to discuss with you my bachelor thesis project that was done in the robotics lab at the Schmalkalden University under the supervision of Professor Frank Schroeder, and my bachelor thesis is titled Concept of an Intelligent Vision-Based Guidance Approach for Industrial Robots Using Model Predictive Control. So, to begin, I would like to discuss with you the focus of this thesis, and it tries to solve the problems that we can see here in this picture, where we have in most typical industrial environments, we have a robot that is isolated in a cage away from the human worker, and there is no cooperation between the two. And the aim of the thesis is to enable human-robot collaboration, and of course, not only a collaboration but a safe collaboration. And this is a desired situation that we see here in the picture, where we see the human worker is collaborating with the robot in a certain task. And usually this task requires the flexibility and creativity of the human worker, and at the same time the precision and repeatability of the robot. And we can see here the robot use these cameras in order to perceive its environment and to locate the human and so on. And the big challenge that usually lies in this situation is the control problem, because if we imagine that we are using a classic controller, so this controller can be a PID controller, for example, where we have a reference here and an error signal, and the classic controller tries to drive the robot towards this reference via this control input. We can see that this classic controller does its job quite well until there is a human in the environment. So if we have a human in the environment, the robot can collide with this human. And of course, this is very dangerous when it comes to human-robot collaboration. We would like to have a desired controller that does the following, where it can, at a certain moment in the present, to plan the path for the robot in the future, so that this robot can follow this path and avoid the human, and at the same time reach its reference at the end. So the desired controller, using image processing and the desired reference, would plan the path for the robot, and at the same time plan the control input in the future that will achieve this path in order to avoid the human and reach the reference. And actually this controller exists, and it's called Model Predictive Control. But as you see here from the name, this controller uses the model of the system in order to achieve each job. So first we have to formalize a complete robot model in order to be used by the Model Predictive Control. And a complete robot model consists of a dynamic model and a kinematic model. And the kinematic model consists of forward kinematics and inverse kinematics. And I would like to discuss with you more deeply the forward kinematics. So this is our IGUS robot that is present in the robotics lab at the university. And this robot is a 5 degrees of freedom robot, meaning that it has 5 joints, and these joints are structured in the following way. And the forward kinematics answers the following question, which is, knowing the angle of each of the 5 joints, what is the position of the end effector in the Cartesian space? And by Cartesian space I mean x, y, and z coordinates, because the end effector has these 3 coordinates. But how to obtain this position in the Cartesian space, knowing the angle of each of the joints, and also not only the position of the end effector but also its orientation, because the robot can achieve the same position in space but with different configurations. So this resembles the orientation. And forward kinematics typically answers this question. And forward kinematics is obtained by following a systematic way called the DH convention, or Deneved-Hartenberg convention. And this systematic way starts by constructing coordinate frames at each of the joints. So these are my coordinate frames. And after that, we have to obtain what's so-called the DH parameters. And these parameters are typically geometric relation between each of two successive coordinate frames. And in order to illustrate the meaning of these parameters, let's focus on link 1. So here is my link 1 that starts from joint from coordinate frame 0 to coordinate frame 1, and we have the coordinate frame 1 attached to link 1, but frame 0 is not attached to link 1 because it is attached to the base, so it is the inertial frame. And let's begin by looking at the R parameter. So R1 is for link 1, and R1 is the distance between Z0 and Z1 along the x0 axis. And you can see here that Z1 and Z0 lie in the same plane, so there is no offset in the x0 direction, and that's why R1 is equal to 0. And the next parameter is alpha1, and alpha1 is the angular distance between Z1 and Z0 along the x0 axis. And we can see here that Z1 can be obtained from Z0 by a 90-degree rotation about the x0 direction. That's why here we have alpha1 equal pi over 2. And D1 is the distance between x1 and x0 along the Z0 axis, and this distance is basically the link length. And finally, the last parameter is theta1, and theta1 is the angular distance between x1 and x0 along the Z0 axis. And it's important to note that theta1 is not constant, because whenever this joint rotates, it rotates by an angle equal to theta1. So this resembles the motor that is installed at each joint that rotates this joint by an angle equal to theta1. And if this joint is rotated, the link will rotate with it, link 1 will rotate, and because frame 1 is attached to link 1, so frame 1 will rotate as well, and x1 will be rotated away from x0 by an angle equal to theta1. And to illustrate the fact that theta1 is not constant, so it is a joint variable, it's called like that. So it is starred in this way. We have a star above theta1 to say that theta1 is a joint variable, and the DH parameters are obtained the same way for each of the other links. And you can see here that each link has a joint variable, which is theta. So here's the column for theta is all starred. And once we have the DH parameters, we can construct what's called the homogeneous transformation. And the homogeneous transformation AI is a transformation matrix that relates frame I with frame I minus 1. And here the C and the S denotes the cosine and sine. So C theta is cosine theta, and S theta is sine theta, and so on. And we can see that this matrix is a function of the DH parameters of link I. So the matrix AI is a function of Ri, alpha I, and Di and theta I. And due to the fact that theta I is not constant, it is a variable, it is a joint variable, so this matrix changes by changing theta I. So it is a function of the joint variable. And after constructing the transformation matrix for each link, we multiply these transformation matrices by each other to obtain the final transformation matrix that relates the end effector position and orientation to the frame 0, which is the inertial frame. And generally, any transformation matrix is an augmentation between two parts. The first part is this 3x1 vector, and this is the position of the end effector in the case of the final transformation matrix. So this is the x coordinate, this is the y coordinate, and this is the z coordinate of the end effector. And again, the C and the S are for cosine and sine. For example, C23 is cosine theta 2 plus theta 3. And the other augmented part is this 3x3 matrix, and this denotes the orientation of the end effector with respect to the inertial frame. And also we can see that it is a function of the joint variables, because each of theta 1, theta 2, theta 3, theta 4 and theta 5 are not constant. They change by changing the joint's angle. So this final matrix is a function of the joint variables. So by that we finish the forward kinematics, and the other part of the kinematic model is the inverse kinematics. And the inverse kinematics does quite the opposite, which is knowing or having a desired orientation and position of the end effector. We would like to know the angular position of each of the joints that would achieve this desired position and orientation of the end effector. And by formulating the forward kinematics and the inverse kinematics, we are done with the kinematic model. And by the way, there is also a kinematic model for the velocity of the end effector, where we address the same question but for the velocity in this case. So for example, the forward kinematic model for the velocity of the end effector is the following, which is, if I know the velocity of each of the joints, what is the velocity of the end effector in the Cartesian space? And this is the kinematic part, and the dynamic part is concerned about obtaining the differential equation of the robot that governs its motion in response to external torques and forces. And for the time duration of this presentation, I think it's enough talking about the robot model. And if you have any question, of course you can email me regarding any question about the illustrated part of the forward kinematics, or if you would like to know more about the dynamics or the inverse kinematics. And now I think it's better to talk more about the model predictive control. So let's imagine we have the following control problem, where we have an initial position for the robot and a desired position of the robot, and we need our model predictive control to plan the path and guide the robot along this path, and at the same time avoid any obstacles that lie along this path. So this obstacle can be an object, can be the human in our situation. And to understand how model predictive control would do that, we need to have a deeper look at its construction and its algorithm. So to begin, here we are here at a certain instant in the present. So this is the present moment at time t0, where the robot is at an initial position, and the model predictive control actually predicts the output of the robot, predicts its behavior in the future, driven by this predicted control input. So how does the model predictive control predict the behavior of the robot? So it does that by using the dynamic model under the initial position at the current instant of time t0. So by using the dynamic models that we have formulated before, the controller can predict the behavior of the robot in the future. So to illustrate the notation here, we have x bar, which denotes the predicted states of the robot. So x bar are the predicted states, and x is the actual states. And the states in this case are the joint angles and the joint velocities. And as I said, the model predictive control uses this dynamic model in order to predict the future behavior of these states. And this future behavior is depending on the predicted control input in the future. So by choosing different control inputs, we would have different future behaviors. And so how does the model predictive control choose the right control input in order to derive a correct output for the system? So this is done based on this function here. So this function is called a cost function, and we can think of this function as an error, but instead of just an error, it is the summation of errors. So this function calculates the summation of all the errors of the predicted trajectory compared to the reference trajectory. And the model predictive control tries to minimize this function by choosing an optimized control input trajectory that would minimize this cost function. And at the same time, the model predictive control can do that while respecting a set of constraints. So these constraints here are constraints for the states. So for example, we can have constraints for the minimum and the maximum angles of each of the joints. We can also have a constraint over the distance between the robot and the human, and of course this distance is a function of the angles of each of the joints, and we can have a constraint on that as well. And also we can have constraints over the inputs, and in this case the inputs are the torques, and we can have a constraint over the torques in order to lie within a minimum and the maximum value. So the big picture of how model predictive control works is that at the current instant, in the present, at t0, the model predictive control tries to choose an optimized input trajectory in the future, and this trajectory is the one that minimizes this cost function, and at the same time the predicted output that is a result of this control input should follow certain constraints that is defined by the user, and also this control input is following a set of constraints involving this input. And after achieving this calculation, the model predictive control is applying only the following control input to the plant. So this control input here is applied, and then these whole calculations are repeated again in the following sampling time. And of course the prediction is achieved for a finite amount of time called the prediction horizon, because the MPC cannot predict the future of the system in an infinite amount of time, so this prediction occurs for a finite amount of time. And I would like to show you also where is the kinematic model involved here. So here we have the reference trajectory, and this reference trajectory can be in the Cartesian space, and as I said, our states are the joint angles and joint velocities, so we have to convert this reference trajectory from the Cartesian space to the joint space. And the same is going as well in the constraints, because the constraints can be defined in the Cartesian space, and we would like to convert it into the joint space. And I would like to show you the behavior of the model predictive control in the following example. So we have here the initial position of the robot, which is defined by 0 angles, and the desired position of the robot is defined by these angles for each of the joints. And I would like to focus on the results of the MPC regarding the fifth joint. So the fifth joint is having an initial position at 0 and a desired position at pi/4, and this is shown here in this graph. So this is pi/4, this is the output, and this is the control input. And you can see here that the model predictive control successfully drive the fifth joint towards its reference value. And I would like to focus in particular on this area here, where we can see that the control input, which is the torque in our case, is increasing as we advance in time, but at nearly the midway between the 0 position and the reference, the torque suddenly changes from positive to negative, although that the joint has not reached its reference yet. And this is because of the prediction mentioned before of the model predictive control, because the model predictive control knows that our system is approaching its reference, so it tries to somehow decelerate the system in order to prevent overshoot or something like that. So to sum up, here model predictive control is used together with image processing in order to achieve this desired situation that we had at the beginning of the presentation, where human and robot collaboration is achieved. And Here, the model predictive control is like the brain of the robot, and image processing is like its eyes. But first, before tackling the model predictive control, we had to realize a complete model of the robot in order to be used by the model predictive control. And then the model predictive control can exploit this robot model in order to predict and optimize the behavior of the robot under certain restrictions. And it's also important to note that there is work that's currently done by my colleagues at the robotics lab, and this work involves image processing and also, for example, installing encoders at the joints of the IGOS robot in order to have feedback. So this work is currently under development in order to bring the MPC or the model predictive control on real hardware. And that's all. Thank you so much for listening. I would be very happy to receive your feedback and your questions if you have any. And also, I would be happy to help if you think that my work can be useful regarding your project. So, thank you all and bye bye.